In this module, we will study the applications of Huckel molecular orbital theory, and we will study this application to ethylene molecule. Application to ethylene molecule would mean that using HMO, we will calculate the wave functions and the molecular orbital energies of the ethylene molecule within HMO approximation. As we have already learned about HMO, that Huckel molecular orbital theory is an approximate method which uses variation method as well as linear combination of atomic orbitals to construct molecular orbitals and then find out the energies and the wave functions of the various orbitals. This theory basically applies to organic conjugated systems. These are the systems which consist of conjugated carbon atoms. And ultimately, the basis of this theory is the sigma and pi electron separability. That means pi electrons can be treated separately. And the basis fact is that the properties of these molecules are primarily determined by these pi electrons. So that is the basis of HMO. Another advantage of this method is that it considerably simplifies the problem. For example, as we will see later on, that in the case of ethylene molecule, which consists of 16 electrons, the whole problem under HMO approximation is reduced to 2 electron problem. And similarly, the same simplification is carried on to other organic conjugated systems. Now, as we have already seen in the last module, that the wave function or the pi molecular orbital in HMO is believed to be the linear combination of pi orbitals. That means, according to LCO-MO approximation, the MO can be written as phi A is equal to summation Ci psi 2pzi, where I is taking a summation from 1 to n. N is the number of conjugated carbon atoms. So this is the trial wave function which is used in HMO, and using this trial wave function, one applies variation method to find out the approximate energy. The approximate energy in this method is given by the following relation: EA is equal to integral phi A star h cap phi A d tau divided by integral phi A star phi A d tau. In this, please note that h is the Hamiltonian and we don't need to define Hamiltonian exactly. This is something very unique in this method. We don't need to define it. We assume that it basically incorporates the effect of the interaction of pi electrons with the rest of the molecule. And in the rest of the molecule, we have both sigma electrons as well as the nuclei. So when this equation is solved, ultimately, as you know, we get a secular determinant whose general form is as follows. This general form will vary from system to system, and if there is a 2 pi electron problem, then this form reduces to the form as H11 minus ES11, then we have H21 minus ES21, and then we have H22 minus ES22, C1, C2 equals 0. This is basically the secular determinant, and as we learned it in the last module, if we substitute the values of Hij, Hii, etc. and Sij and Sii, etc., then this secular determinant reduces to the following form. You can see here the secular determinant now looks like alpha minus E, beta alpha minus E, secular determinant is equal to 0. Here alpha, as you already know, is basically the Coulomb integral, which is assumed to be same for all the carbon atoms. and beta is the resonance integral, which is basically, as you can see here, for carbon atoms which are directly connected is having the value of beta, and those carbon atoms which are not directly connected, it's basically assumed to be 0. Now, the whole problem in HMO basically reduces to solving this secular determinant. In a general case, we have a secular determinant of the order n by n. If we expand it, we get a polynomial equation of order n, and its solution will give n roots. And from those roots, one can calculate the energy of the various n orbitals. In general, the energy of the nth molecular orbital is expression Ea is equal to alpha plus xa beta, where xa is the nth root of the polynomial. So in this way, we are able to get the energies of the various pi molecular orbitals in HMO. And using these results, one can also calculate the corresponding wave functions representing these energies. So that's basically how the entire HMO theory operates. And now we will apply it in a clear form to a very simple molecule, and that is ethylene. Let's now study the application of HMO to ethylene molecule. Ethylene molecule, as you all know, consists of 2 pi electrons and has one double bond. Look at the structure of ethylene molecule. In total, ethylene molecule has 16 electrons, as you can see here. But in HMO theory, this 16 electron problem reduces to 2 pi electron problem. That's a very big advantage in HMO. If we label the 2 carbon atoms of ethylene molecule as 1 and 2, then the corresponding secular determinant using HMO in the case of ethylene molecule reduces to this form. The secular determinant, as you can see, has the first row H11 minus ES11, then we have H12 minus ES12, and the second row is H21 minus ES21 and H22 minus ES22. And then we have C1 and C2. These are the 2 variable parameters which will ultimately determine the wave function or the pi molecular orbital. Please note that the pi molecular orbital is constructed using the principle of LCAO, and in this case the corresponding molecular orbital is given by the general expression phi A is equal to C1 psi 2 pz1 plus C2 psi 2 pz2. Please note here that 2 pz1 is the pi orbital centered on carbon atom 1, whereas psi 2 pz2 is the pi orbital centered on carbon atom 2. I don't need to mention it again, but as I have already mentioned it earlier, we are assuming the molecule to be in the xy plane, and therefore these pi orbitals are in a plane perpendicular to the xy plane, that means along z orbital, z axis. Now once we have this secular determinant, and in this if we use the approximations of Huckel, that means replacing the corresponding integrals with Coulomb and resonance integrals, then this secular determinant reduces to Huckel determinant, and the form of the Huckel determinant is as shown. The first row becomes alpha minus E beta, and the second row is beta alpha minus E C1 C2 equals 0. So that's basically the Huckel determinant which we have. And now in this equation, since C1 C2 is not equal to 0, therefore the corresponding equation becomes alpha minus E beta, beta alpha minus E, and this is the Huckel determinant, which is now equal to 0. Now this is in this case a 2 by 2 determinant and we need to solve it. But before we solve it, we make the following assumption. We substitute alpha minus E upon beta equals lambda. And if we substitute this value, the corresponding Huckel determinant reduces to, so the Huckel determinant becomes lambda 1, 1 lambda, and that has to be equal to 0. This determinant on expansion gives us this equation, which is lambda square minus 1 is equal to 0, and which on solution gives two values, lambda is equal to plus minus 1. So these are the two values we get. And if we substitute back into the main determinant, we get the corresponding, the following equation. So you can see here that if we substitute the value of lambda is equal to minus 1 and lambda was equal to alpha minus E upon beta, then we get the energy of the orbital, which becomes equal to alpha plus beta. And similarly, if we put the second value of lambda, which is equal to 1, we get the energy of the orbital, which becomes equal to E is equal to alpha minus beta. So these are the two values of the pi molecular orbital energies which we get from the corresponding HMO solution. Please note here that we are getting 2 pi molecular orbital energies, and please note that the number of molecular orbitals that are generated using LCO approximation are always equal to the number of combining atomic orbitals. Since you also know that both alpha and betas are always negative, therefore using these energy level expressions, one can write or draw the corresponding energy level diagram for ethylene molecule. As you can see here, at the lower end we have bonding molecular orbital, which represents the energy E is equal to alpha plus beta, because alpha is also negative, beta is also negative, so the total expression will be negative. That means it leads to stability, and therefore it is called bonding molecular orbital. And then at the top we have E is equal to alpha minus beta, which is referred to as the anti-bonding molecular orbital. Please note here that since there are only 2 pi electrons in ethylene molecule, as you can see from this diagram, both these electrons are accommodated in the bonding molecular orbital, and that anti-bonding molecular orbital is vacant. One can also notice from here that since both the electrons are in the bonding molecular orbital with energy alpha plus beta, therefore the total pi bond energy of ethylene molecule will be 2 alpha plus 2 beta. That's very, very important. Now, after having calculated the energies of the pi molecular orbitals, one would be interested in knowing the corresponding wave functions which correspond to these molecular orbitals. For this, we go back to our main equation which we had already derived. We now need to solve the corresponding secular equations to find out the wave functions. And wave functions can be obtained if we know the values of C1 and C2. So if we solve these secular equations, as you can see here, we get two equations which on further simplification lead to the fact that if lambda is minus 1, then C1 is equal to C2. And if lambda is plus 1, then C1 is equal to minus C2. So these are the values of the two coefficients which were used to have the linear combination of the orbitals. But then we have to ensure that the wave functions are normalized. Therefore, we apply the normalization condition as shown. If the wave function has to be normalized, then you will agree that this integral phi a star phi a d tau has to be equal to 1. If we substitute the LCO expression for phi a star and phi a, we get this equation, which on further simplification gives us the corresponding values which have been derived, which if we use the corresponding expression for phi a, it becomes C1 psi 2p z1 plus C2 psi 2p z2 whole square d tau is equal to 1. If we solve this integral, as you can see here, ultimately we get the value of C comes out to be plus minus 1 upon under root 2. This is the value of C which we are getting after applying the normalization condition. Now the results of our calculations for ethylene molecule have been summarized in this table. As you can see from this table that for the bonding molecular orbital, lambda was equal to -1 and the corresponding energy of the pi molecular orbital is alpha plus beta. And the corresponding values of C1 and C2 both are equal to 1 upon under root 2. And there is no node. That means, as you can see, there is no node in this. Both are having a positive coefficient C1 and C2. In contrast, in the case of anti-bonding molecular orbital, lambda was equal to 1 and the corresponding energy of the pi molecular orbital is alpha minus beta. The values of the corresponding coefficients as we have calculated are C is equal to 1 upon under root 2, which is C1, and C2 is minus 1 upon under root 2. And there is one node here. So the results have been summarized here. So now you can see that the wave function for the bonding molecular orbital will be 1 upon under root 2 psi 2pz1 plus psi 2pz2. And the wave function for the anti-bonding molecular orbital would be 1 upon under root 2 in parenthesis psi 2pz1 minus psi 2pz2. Using these wave functions for both bonding and anti-bonding molecular orbitals, the corresponding pictorial representations of these Huckel pi molecular orbitals can also be made, and these are shown in this diagram. We will also calculate here a very interesting quantity which is called the pi bond formation energy. As we have seen in our calculations that the total pi energy of ethylene molecule is, because both electrons are in the bonding molecular orbital, the total energy is 2 alpha plus 2 beta. That's the total energy of ethylene molecule. But had there been only two separate atoms, then the total energy would have been 2 alpha. Therefore, the pi bond formation energy would be the difference between these two. Therefore, the pi bond formation energy becomes the energy of the ethylene molecule minus the energy of two isolated carbon atoms, and that becomes therefore 2 alpha plus 2 beta minus 2 alpha, that means 2 beta. And since beta is a negative quantity, therefore when two isolated atoms come and form ethylene molecule, the system gets stabilized, and the amount of energy by which it gets stabilized is equal to 2 beta. So to summarize, what we have learned in this module is how one can apply HMO to a simple conjugated molecule, that is ethylene. HMO, as we have learned, is basically an approximate method to treat organic conjugated systems. The basic assumption of this method is that the properties of these molecules are primarily determined by pi electrons, and therefore one can have the pi electrons separated from sigma electrons and the rest of the nuclei. In this method, we have used variation method and the LCO-MO to construct an approximate wave function. We applied this method to ethylene molecule, and we found that the wave function for the bonding molecular orbital is equal to 1 upon under root 2 psi 2pz1 plus psi 2pz2, while the wave function for the corresponding anti-bonding molecular orbital is 1 upon under root 2 psi 2pz1 minus psi 2pz2. We also noted that the energy of the bonding molecular orbital is alpha plus beta, and that the corresponding total energy of the ethylene molecule, pi electron energy, would be 2 alpha plus 2 beta. We also gave the concept of pi bond formation energy, which is the energy difference between the energy of the ethylene molecule and the corresponding energy of two isolated carbon atoms. And we found that this energy comes out to be equal to 2 beta. In the next module, we will study the application of HMO to other organic conjugated systems, and the same principle and the same procedure will be applied to other systems which are somewhat more complex than the simple ethylene molecule.